Okay, now that we have the factor theorems and the fundamental theorem of algebra, let's talk about partial fraction decomposition. We'll see how to integrate these partial fractions in the substitution video. So I just want to do just partial fraction decomposition and not worry about the integral part. So partial fraction decomposition deals with rational functions. And so you have a, let's say, n of x for the numerator of x and d of x for the denominator or the divisor of x. And these are both polynomials. Okay, and we say that this is a proper fraction if the numerator has a lower degree than the denominator. This is proper if the degree of the numerator is less than the degree of the denominator. Okay. And we can always put this into a nice proper fraction form by using the division algorithm. And so I do polynomial division and I get that n of x over d of x is equal to a quotient polynomial plus a remainder polynomial divided by the divisor polynomial, where where r of x in degree is less than the degree of d of x, right? This is very analogous to the division algorithm with integers. And let me just show you how this works. So if I had 7/3, I could rewrite that as the quotient. Well, 7 divided by 3 is 2, plus I have a remainder of 1. And so this 7/3 is actually 2 and a remainder of 1/3. And my remainder has to be smaller than my divisor in integer division. Well, the degree of the remainder has to be smaller than the degree of the denominator in polynomial division. And this works out just fine for us. If we were to do integration, what I could do if I wanted to integrate this, I could integrate these two pieces instead, and this is just a polynomial, so polynomial integration is easy. And then I just have to deal with integrating a proper fraction rather than just any fraction. And integrating proper fractions is easier because, well, we can use this partial fraction decomposition on proper fractions. Okay, so let's sort of step through this a little bit. Let's do an example to start with and then sort of write out the steps that we're going to use. So we want to write, say, x plus 3 over x plus 1, x plus 2 as a partial fraction decomposition. Okay. So what that means is I've got these factors in the denominator, and the denominator looks like it could have been the common denominator for an addition problem. The addition problem being maybe I had a over x plus 1 plus b over x plus 2, and if I get a common denominator down here, this is going to be a times x plus 2 plus b over x times x plus 1 all over x plus 1 times x plus 2. And that's great because I've got sort of a linear polynomial here plus a linear polynomial here is equal to a linear polynomial. It's a proper fraction, so I could probably figure out what a and b were to make this equation true. And that's what partial fraction decomposition is. So now I've got this set up, and we want it to be x plus 3 over x plus 1 times x plus 2. So I can solve this equation to figure out what a and b were. Well, usually equations have in two unknowns, we need two equations for them, but I've got two unknowns, and I do kind of have I've got an equation of polynomials here. And the polynomials, well, polynomials match up in a few ways. Polynomials match up if their coefficients are all the same, they're equal polynomials. If they evaluate to the same place at any input, if any input gives you the same output, the two polynomials are the same as functions. And if their derivatives are all the same, they're the same function. So there's kind of three ways that polynomials can be equal, and each of those ways gives us a way to solve these. So let's look at this. If they're also equal if their integrals, well, if their integrals differ by a constant, then they're equal. But that's sort of that's a trickier thing. So we're just going to go with they have the same coefficients. So let's go with they have the same coefficients. So I've got the x coefficient, or the x terms are ax plus bx equals 1x. So on the left hand side I've got ax plus bx, and on the right hand side I've got x. That gives me an equation in the two unknowns that says that a plus b equals 1, and then I've got a constant term where I've got 2a as a constant on the left plus b as a constant on the left is equal to 3. So I need to solve these two equations simultaneously, and let's subtract the first one away from the second one, and I would get that a is equal to 2, and if a equals 2, b equals -1. Okay, so that's sort of the first way to do this. The next way to do this is let's evaluate at certain points. Let's evaluate at x equals -2. If I evaluate at x equals -2, this first part becomes 0, and I get that negative b is equal to 1, which tells me b equals -1. Right, if you put -2 in here, you get -1b. If you put -2 in here, you get +1. So you get this equation. And let's say if I evaluate at x equals -1, then I get that a equals, well, -1 in here gives me 1 times a, gives me a 0 there, and gives me a 2 there. So that gives me the same solution that we had. Now I chose these two evaluation points because they were going to cancel with a lot of the parts of the fraction, or the expressions. They would make zeros in places. You don't have to choose places that are going to make it 0 to get an equation. I would perfectly well have chosen that x equals 0 and gotten that 2a plus b equals 3 as an expression that I would want to use. I mean, that expression is right there. It's a perfectly valid equation that I could have used to solve these things. Okay, now the other place is if all of their derivatives are the same. And all of their derivatives are the same, it's just saying that two new polynomials are equal. So I still have to sort of combine it with one of these other two techniques. I can differentiate and then evaluate at points, or I can differentiate and set up terms being equal. So let's look at that. So if I differentiate the left-hand side, I get a plus b equals 1. If I differentiate the left-hand side, I get a plus b. If I differentiate the right-hand side, I get just 1. So that gives me an equation, and I can't differentiate this anymore. That gives me 0 equals 0, and that doesn't tell me any more new information. But this differentiation gives me one of the equations that I could use. And when we have higher degree pieces of the polynomial here, this differentiation can be used as well to get more than just one piece of information. So I'll use this piece of information, and maybe that b equals -1 from this evaluation at -2 in the first place, and putting these two things together, you still get that b equals -1 and a equals 2. Okay. So those are kind of our three methods for doing this. Let's sort of write out what actually happens when we're doing this in general. Okay. So if I have a p of x over, let's go with an n of x over d of x, and it's in proper form, our fundamental theorem of calculus, proper and simplified, these things don't have any common factors. If you have common factors, you'll end up, well, let me show you what happens if they have common factors. So let's say I have x squared plus 2x plus 1 up here, and I've got x plus 1 and x minus 1 down here. So if you notice, this is equal to x plus 1 squared over x minus 1 times x plus 1. So I didn't simplify this because I could have taken out a factor from the numerator and the denominator. But let's try and take the partial fraction decomposition of this thing as it's written. Let's go with a squared there so that I actually have a proper fraction. So I would probably want this to look like a over x plus 1 plus b over x minus 1 plus c over x minus 1 squared. These are linear factors, so I have constant coefficients here, and we'll explain that in a little bit. But when I do this, I get a times x minus 1 squared plus b times x minus 1 times x plus 1, and then I've got c times x plus 1. And I want that to be x squared plus 2x plus 1. Okay, let's see what happens. So if, let's say x equals 1 is where we're going to evaluate at to get an expression. So if I put x equals 1 in there, I get 4 equals, well, that's going to give me a 0, and 2c. So c equals 2. Let's do x equals -1. If I put -1 in, I get 4a, the left hand side. If I put -1 in there, I get 0 equals 4a, -1, those are 0. So this tells me that a equals 0. Okay. I still have to figure out what b is. So let's differentiate and see what happens. So I get 2x plus 2 is equal to a times 2x minus 2 plus b times x minus 1 plus x plus 1 using a product rule, and plus c. So you get 2x plus 2 equals a times 2 times x minus 1 and plus b times 2x plus c. I want an expression with b in it, so let's just pick x equals 1. I get that 4 equals 2b plus c. This tells me that b equals 1. So now I get a equals 0, b equals 1, c equals 2. So a over x minus 1 plus 1 over x plus 1 plus 2 over x plus 1 squared. I think that's what I had. Yep. Well, that tells me that x minus a is 0. I don't even need this x minus 1 piece. How am I supposed to get this as a part of the common denominator then? Well, that's sort of where we find out that this piece wasn't actually needed, because this x plus 1 in the denominator, it canceled out with the x plus 1 in the numerator, and so that piece wasn't actually there. So it does work out fine if you don't reduce, but it makes your work quite a bit harder, because you need to figure out, well, you're adding an extra variable that you already know should be 0, or multiple extra variables that you already know should be 0 if you had actually done the simplification first, or the reduction first. Okay, so let's again look at numerator of x over denominator of x, and we'll assume that these are as proper and simplified. Okay, we're going to factor the denominator, and we're going to factor the denominator into linear factors. Let's say x minus the first root to the multiplicity of it, and x minus the second root and the multiplicity of it, and dot dot dot, x minus the kth root and the multiplicity of it. And then I've got these other quadratic factors, which are sort of, I'm going to write as x minus ci, x minus ci bar to the their multiplicity. Let me call their multiplicities n's instead of m's. And we do that until I get all of them. And so I get x minus ci, x plus ci, or no, not plus, x minus ci, x minus ci bar. And this is raised to the nj power. Okay, so we have this thing that's factored, and I've still got the numerator on top, which I don't need to factor. Okay, what we can do then is, for each of these pieces, this piece, it's going to turn into the sum of x minus ri, well, this is the first one, so r1 to the k, and I'm just going to put an a sub k over it. This is going to be an unknown, and this is going to go from k equals 1 to m1. And the next one is going to be the sum, say bk over x minus r2 to the m to the k, where k equals 1 up to m2. And we do that for each of these factors. X minus r, I'm going to go with a j there, and mk, nope, that's a k, and this is going to be another, I don't know, variable. This is k, j. Okay. So for each of these, I get one of these things, right? And then for these quadratic factors, we also have to do something similar. For the quadratic factors, if I have, say, 1 over x minus ci, x minus ci bar to the third, for example, we'll do something very similar. We'll write this as ax plus b over this thing. I'm going to call it star over star, and then plus cx plus d over star squared plus ex plus f over star cubed. And so I have to do this 3 times because the multiplicity of this factor is 3. But here I have to use linear factors instead of constant factors. For linear terms I have to use constant factors. For quadratic terms I have to use linear factors. And the reason for that is because now these are going to each be proper fractions, and when I add the proper fractions together I should still get a proper fraction. But this thing could have, like, to still be a proper fraction, this thing could still be up to degree 5, right? I have the opportunity of having a degree 5 thing on top of this piece. Well, how do I get degree 5 parts out of this? I've got degree 1 things on top. I should have degree 5 things. Well, when I multiply to get a common denominator over here, I have to include 2 more of these things here. That's going to be degree 4 times degree 1, which is going to be degree 5. So you get the degree 5 piece from this A, you get the degree 4 piece from the B, you get the degree 3 piece here from C, because you have to multiply this by a degree 2 thing on top and bottom. So you get degree 3, degree 2, degree 1, and degree 0. And that's how these all kind of work out. Right? This piece here, it can have up to degree m1. Well, I have degree 0s all throughout, but when I create this proper fraction, or when I create the common denominator, I have to multiply each of these degree 0 pieces by some number of x minus r1s. And that's going to give you all those extra degree pieces. Okay. So let's do an example of something with a repeated quadratic, because those seem to be the hardest. So let's look at trying to get a proper fraction decomposition of, let's just say, x plus 1 over x squared plus 4 to the third. So let's try and get a proper fraction decomposition for this. It's already in proper fraction decomposition form. So let's do x cubed plus 8 over x squared plus 4 cubed. Okay. So now I've got degree 3 over degree 6, and let's see how this is going to work for us. Proper fraction decomposition form, I should have sort of an ax plus b divided by x squared plus 4 plus a cx plus d over x squared plus 4 squared, and then an ex plus f over an x squared plus 4 cubed. Okay. So now what I need to do is I need to write the right hand side with the common denominator. So I get ax plus b, and I'm just going to look at the numerator if I would do that. You get x squared plus 4 squared, and then you get cx plus d times x squared plus 4, and you get an ex plus f, and that's going to be x cubed plus 8 is the other numerator. Okay. So I do have my degree 5 part here, my degree 4 part here, my degree 3 part, my degree 2 part, my degree 1 part, and my degree 0 part. Okay, so this has everything that I would need. If this was degree 5, I could still get the degree 5 pieces from over here, and so on. So let's go through and see if we can get some of these things. Evaluation, I could evaluate at 2i or negative 2i, but that would deal with complex numbers, so maybe evaluation is something I don't want to do with this one. Let's look at the degree 5 piece. So the only way to get degree 5, so x to the 5th term, I would have to take x squared times a. So ax to the 5th. I can't get x to the 5th any other way, so ax to the 5th is 0. This tells me that a equals 0. Okay, x to the 4th term, also, the only way to get x to the 4th is looking at b x to the 4th here. Highest thing here, this is degree 3, this is degree 1, so bx to the 4th is the only way to get that, and that's also 0. Okay, so I know that I didn't need this piece. This is a 0. This guy's 0. Still, I get these other guys that might not be 0. So I can kind of just ignore this thing completely now that I know it's equal to 0. And then over here, let's try and find the constant term. The constant, 4d plus f equals 8. Okay, that gives me a good relationship that I can use. How about the x term? I can get an x term from 4c. I can't get an x term using d, and then I get plus e equals 0. I can get an x squared term. I can get x squared from d, and that's the only way I can get x squared. So d equals 0. It tells me that f equals 8. So I get d equals 0, f equals 8, a equals 0, b equals 0. How about the x cubed term? And that would give us all of them. X cubed, the only way to get x cubed is c. C equals 1. So my decomposition is going to be 1 over x squared plus 4 squared plus 8 over x squared plus 4 cubed. Let's just check that makes things work for me. What do I need? I need to include an x squared plus 4 times 1 plus 8. Did I do something wrong? I thought I had just an x cubed plus 8. I'm going to get an x. This is an x. Okay. Oh, I never solved for e. E equals negative 4. Okay, so I get negative 4x plus 8. There we go. I like that. I think a little bit better. Yeah. So that's that plus negative 4x plus 8 over x squared plus 4 cubed, and that's equal to that's an x. So that's x cubed plus 4x minus 4x plus 8 over x squared plus 4 cubed. Those cancel. Works out fine for us. One thing about the differentiation rules. So let me do a one with linear terms. Let's say I've got x cubed plus x plus 1 over x plus 1 cubed x minus 1 squared. So degree 3 over degree 5, I want to write this as a over x plus 1 plus b over x plus 1 squared plus c over x plus 1 cubed plus d over x minus 1 plus e over x minus 1 squared. So I get that I have a x minus 1 squared x plus 1 squared plus b times x plus 1 times x minus 1 squared plus c x minus 1 squared plus d x minus 1 x plus 1 cubed and e x minus plus 1 cubed equals x cubed plus x plus 1. Alright. Differentiation does not remove roots. So in here, well, it removes one of the roots. So if I have multiplicity 2, the derivative of this will have a root of multiplicity 1 at negative 1 and a multiplicity of root of 1 at 1. So because the multiplicities of both of these are 2, their derivatives will have a root at 1 and negative 1. This guy, the derivative will have a root at 1, but it won't have a root at negative 1. This one, this will have a root at 1 when you take a derivative. This one will have a root at negative 1 when you take a derivative, and so on. This will have a root at negative 1 when you take a derivative. So if I want to differentiate with respect to x all of this stuff and evaluate at x equals, say, 1, because this has multiplicity 2 at 1, I don't have to worry about this entire piece. This entire piece will be 0 when I evaluate at 1. This piece also has multiplicity 2 at 1, so that'll be 0. I won't have to worry about that. That will also be 0. I won't have to worry about that. The derivatives that I'll have to worry about here are these two, and so this will equal the derivative of the d piece, so d times, so this is not d sub x, this is my variable d here, and then I get to use the product rule, so I've got an x minus 1 times 3 x plus 1 squared, which will go to 0, and plus x plus 1 cubed. So that part goes to 0 at 1. I just get x plus 1 cubed, so this is going to be 8d plus this piece here. It's going to be e times 3 times x plus 1 squared, so plus 12e. So this is 8d plus 12e. If you evaluate the derivative with respect to x at 1, you get this, and so that should equal, on the right hand side, if I differentiate and evaluate at 1, I get 4. So that's sort of something that you can use on these linear guys. Let me just show you why that happens. Okay. Suppose p of x has x minus r squared as a factor. Then the derivative with respect to x of p of x is equal to, well, the derivative with respect to x of x minus r squared times whatever the quotient is, right? And there is no remainder because this is actually a factor. So that's going to equal, by the product rule, 2 times x minus r times q of x plus x minus r squared q prime of x, and that's going to equal x minus r times 2q at x plus x minus r q prime at x. So I've got this factor that sticks around. I don't know what happens in here, but I do have a factor that sticks around there. So the evaluation at that root is going to be 0. Right? So if I evaluate this thing at x equals r, you get 0. And so you can kind of ignore the multiple roots when you evaluate at certain spots, and that allows you to compute these, use this derivative to compute some expressions a lot faster. Okay, that's probably enough for partial fraction decomposition.